Welcome back to CSC241 Computer Architecture. Today is Monday, the 23rd of October. We're all breathing a sigh of relief after Hurricane Tammy decided to be a no-show for the ball. And she turned north and left at the stroke of midnight over the weekend. And there was a little bit of soggy, but not too bad. So we're relieved. Does everyone see the 3.4 reconciliation that's been posted?
Yeah.
All right. In the resources folder after class, I will post the item analysis that we walked through on Friday for
Excuse me,
yes.
you said the module two?
Now this is for module 3. Oh, I said
Oh,
module 2? Yeah, if I said module 2, that was maybe I need another cup of coffee. I'm sorry. This is the reconciliation for the module 3 assessment. Yeah. So the module 3 assessment, we reviewed the first attempt for students that completed it on Friday. So we went through that item analysis. The recording for that will be linked after our class today if you need to access that. If you were there in class, you already know the items, but what we'd like to do is get this and the retake out shortly so that you can complete those before the end of the week. So that's one thing we'd like to call out before we move on to module 4. Module 4 and Rosalina, did that response satisfy the interest?
Yes, but I was wondering about module two if the assessment was ever posted again.
Module 2 final assessment and module 3 will be posted this week, and you'll have the week to complete those. So thank you for answering that or asking
Okay,
that. Yeah.
thanks.
Yes. Once again, module 2 and module 3 final attempts need to be logged before the week is out on Saturday, 11:59 p.m. And we'll be posting those. Be sure to complete the reconciliation before you do that. What you see today is the cover page for our module 4 content in Blackboard. We're going to be getting into the actual physical hardware. So to me, the theory of logic gates and how you can use them to create complex logic gates to build digital components is half the charm. But then once those components are specified, that's when the real magic happens. So we take those digital components and then we build things like memory chips and CPUs and motherboards and so on. So that's the focus of module 4. Please stand by. Just want to update the roster here yet. In this module, apart from the hardware components that are used, we'll be talking about the classic computer architecture model devised many decades ago by a pioneer named John von Neumann. This model for computer architecture remains in play, and it's used consistently for all devices and systems that have any computing capacity whatsoever, right? So it's really important to understand that I want to say 40 or 50 years ago, a long time ago in a galaxy far, far away, a pioneer named John von Neumann figured out and organized how computers are really supposed to be built. And it's those components or building blocks that are consistent for everything we use and know today. We'll also be taking a good bit of time to focus on the materials and the science for those materials behind the electronic components. So as we're looking at the hardware itself, how are computer chips built, and what are motherboards made of, and so on. Specifically, our learning outcomes include the capacity for each student to be able to explain how physical materials can be used to build electronic logic gates and chips. So we've been using the design simulation environment in order to prototype a chip. But in fabrication facilities, they're not called factories, they're called fabrication facilities. The simulation of the hardware HDL code is fed into other equipment, and it results in the creation of the physical chip or the physical component. It's actually really cool. So what you've been using so far in the HDL simulation is the first step, but then we go to the factory. Again, it's called a fabrication facility. And where chips are fabricated and digital components are built. And it's there that the HDL can be translated into an actual physical design. Any questions on that particular interest? We want to retrace the development of innovative digital components. We've already talked about the MUX, but there's another one called the DFF, and it's the digital flip-flop that allows for memory. So memory chips, without certain components, without a computing module, a CPU, and without memory, you wouldn't have it, right? So we're going to be talking about how a digital flip-flop is used to build a memory register. We'll also turn our attention to the CPU, the full adder. Adder is the term that was used for the first CPU. DSPs, digital signal processors, and universal asynchronous receiver transmitters, or UARTs. So these are the communication components that allow for networking so that everything can be connected together. We want you to be able to contrast the two types of logic gates. So to this point, we've been talking about combinational logic gates. We've been combining logic gates to build compound logic gates and then complex logic gates. But essentially, you reach a tipping point where the digital components have to include a component. It has to include some way of measuring time or working tasks with a given interval for a given interval. So as soon as you start talking about ordering the operation of those logic gates, when you order the operation of those logic gates and you do them in a specific order, first, next, and last, what's implied by that is this idea of time or sequence, or both, actually. You wouldn't have a sequence if you couldn't figure out what comes first, what's performed next, and then what's calculated last. And it's often been said that time is God's way of making sure that everything doesn't happen all at once. So we're going to take a deeper dive into a special class or category of logic gates that allow for timing to occur. And then we're going to give you examples of those. A system clock would be a great example of that. So we'll be spending quite a bit of time reviewing and analyzing system clocks. We want you to be able to analyze the internal components and digital actions along a certain path if we give you a diagram. So that's one of the goals of our module. And then finally, we want you to be able to design a complex logic gate using 3 or more different components that must include a NOR, NAND, XOR, and XNOR. And you're probably saying, hey, wait a minute, that sounds really familiar. Well, you get a chance to redo or recast your first solution. Your second solution in module 3 you get another chance to do it again and do it better and faster if that's of interest. Any questions about the overview of Module 4? Could someone unmute your microphone and let me know we're still there?
Yeah, we're still here.
Yes.
Okay. So let's take a quick look at our first learning objective, right? Physical materials used for logic gates, electronic logic gates, and physical digital components. So when we're building physical, real hardware, not the logical components in a simulation environment, right? The term transistor. Has anyone ever heard of the term transistor before?
Yeah, I have.
Yes. So a long time ago in a galaxy far, far away, your grandparents, or actually your great-grandparents, were the first to experience things like radios and televisions. And the radios and televisions were first built with something called a vacuum tube. A vacuum tube was a digital component that would switch on and off, and much like a logic gate would switch on and off, except that vacuum tubes were, well, they were costly. There was a lot of material that went into them. And in fact, if we look at the earliest examples of hardware components, vacuum tubes. Has anyone ever seen something like this when you look in the back of a radio or a TV?
Nope.
No, it's unlikely. You'd have to go to a museum and find a really old TV or a really old radio. Back in the 30s and 40s, radio was the most common way for people to communicate with electronics. And so the first radio stations would broadcast programs. And so this was a big deal in the late 20s, early 30s, and 40s. Now, as time went on, they started to realize we could use the switching capabilities of vacuum tubes to create the first computer. And so the first computers that were built out of these vacuum tubes would take up an entire building. So I want you to imagine a building at UVI campus existing for the sole purpose of housing a computer, a single computer, the mainframe computer for the university, an entire building, right? That's how the first computers were built. Now, of course, because of the construction, there's literally a vacuum. There's no air inside here, and there are electrical components inside there. And it's how this thing works to be able to switch on and switch off. So ones and zeros, switching on and switching off. Any questions about vacuum tubes? So after so many decades of working with expensive and impractical and very large things, electronic engineers and electrical engineers devised and realized that there were certain materials that conducted electricity on conditions, based on conditions. Now, let me say that again. There were conductors that would allow the flow of electricity based on certain conditions. We would call these semiconductors. Has anyone ever heard of the term semiconductor?
Yes.
Thank you. Semiconductors, right? So what scientists, material scientists began to understand, and this again occurred over decades, right? The vacuum tubes that could be switched on and off could be replaced by materials that would allow the flow of electricity based on certain conditions, right? So they were conductors, but not just wire. If you have just wire, you have a conductor. But if you have certain materials in the periodic chart, okay, in the periodic chart of elements. So let's look at that real quick. Does this look familiar to anyone?
Yes.
You may have had a science class where you're learning about chemistry and the elements, and many of our elements are metal. And because they're metal, they're conductors. They just allow the flow of electrons. And then there are elements that are non-metals. They do not allow the flow of electrons whatsoever, or the flow of heat. So metals allow not only the flow of electrons, but also the flow of heat. So heat, you can heat up something like copper, and it won't take long before the heat travels down the length of that metal or across that metal. That's why copper is used for cookware. This is something you already know and you use every day. Aluminum, you have aluminum pots and pans, right? And then there's tin, right? So there's all kinds of metals that we use, we know. But then what about the non-metals? Those are called insulators. Technically speaking, they block the flow of electrons. They're thirsty for electrons, and when electrons come near, well, these elements tend to snatch up the electrons, and they prevent the flow of electricity, prevent the flow of electrons. So whenever you have a flow of electrons, you have electricity. And whenever you have something that blocks the flow of electrons, you have a non-conductor, or another way of describing that is insulator. We insulate our wires with plastic, and plastic is made out of carbon, right? And so there are carbon compounds that are used to create plastic, and plastic is used basically to insulate wires so that the electricity doesn't hurt us. It keeps the electricity from jumping off the wire and through us. Any questions about conductors and non-conductors at this point? Going once. Going twice. Has anyone ever worked with conductors and non-conductors to create a circuit or build a circuit before?
No.
So it used to be in science classes that the science teacher would pull out some batteries, a light bulb, and some wire, and then people would learn how to set up a flashlight, build a flashlight. Has anyone ever built a flashlight out of raw materials before?
Yeah, I have. Well, not a flashlight, but like just let the bulb get lit.
Yes, yes. So any light, not necessarily a flashlight, but the light, like the lights in your house, yeah. Okay, so the wires are protected or coated with a non-conducting material, we would call an insulator. And then in between, so there's a diagonal line here. All of these to the left are metals. Most of the elements on the periodic chart are metals: zinc, nickel, cobalt, iron. If we mix iron with copper, we get, iron with carbon, we get steel. So actually, iron is, the iron ore is heated up in a furnace with coke. Coke is like charcoal. It has carbon in it, and the carbon mixes in with the iron and it becomes stainless steel. That's where steel is from, right? We can also have steel that has other things mixed in with it, right? So we can have other types of alloy that harden the steel or harden the metal. We have chromium and manganese and all these cool metals, right? Gold. So gold is one of the most conductive of all metals. And silver, where is silver? Silver and gold and copper, this family in particular, are ideally suited as conductors. So that's just something to understand. They're in the same column here. And because of the structure of the atom, copper and silver and gold are considered the three most conductive metals around. Now, in between the non-metals here, and these are inert elements, that means they don't do anything. The neon gases, helium, neon, argon. In between the non-metals and the metals is an area of the periodic chart called semiconductors, right? So when you look at silicon and oxygen together create much of the raw material, silica, for our chips. So silicon is a semiconductor, meaning it allows for the flow of electrons under certain conditions. I want you to notice too that there's gallium and arsenic, or germanium and arsenic. Those are also semiconductors, and every now and then you'll see something about chips and digital components that are made out of gallium arsenide or germanium, and those are semiconductors. There are actual CPUs that are created out of those, not very often, but silicon by far is the least expensive and most plentiful of the semiconductors. This is just something we really want to understand on a simpler basis. So when we have the semiconductors, we can take those same vacuum tubes that switch on and off, that provide for ones and zeros, and instead of having slow heat producing components, now we have something that's actually very plentiful, and it's much higher performance. And so these transistors are basically created out of semiconductors, silicon, right? And yes, there's metal that's embedded in the silicon. And there are different types of transistors. And in particular, there's an NPN and PNP. So if you take the materials, one of the materials allows for more readily allows for the flow of electrons, and the other one resists it. Has anyone ever heard of the term resistor?
Yeah.
Yeah. Capacitor is a digital component that stores electric charge, much like a battery, sort of like a battery, but different from a battery. So, we think of batteries and use batteries all the time, but there's a related device called a capacitor that stores up a certain amount of charge, and it's short-term. Basically, it's more controlled storage and higher capacity storage of electrons. When you see something called ICs, IC is an acronym. It's an abbreviation for a phrase, integrated circuits, right? So when you take these transistors and you combine them, it creates circuits. And if you integrate the circuits, now you have a chip. So by the time you finish integrating the circuits, you kind of hit the tipping point where instead of talking about integrated circuits, the common term for chip, you'll hear that everywhere. Here's a chip, it's a memory chip, or here's a computer chip. The most important thing to understand, though, is that just like logic gates, the basic transistors, there are basic component transistors that are used to build the bigger chips. Just like we can take logic gates and create very complex creations. That's the same kind of thing. So here is a hint about where we're going with this. There's an N type of material, a P type of material, and an N type of material. NPN. And it is the NPN type of transistor that is the physical equivalent of one of our logic gates, NPN. The reverse of that, PNP, is the other type. So if you take this N type of semiconductor material, the P type, and then sandwich it between the N types, that's one kind of transistor. And then the reverse of that is the other type of transistor. And between those two types of transistors, that's where our digital components can be created to work like our logic gates, okay? So the important thing to understand is that at its most basic level, transistors, the two basic types of transistors, NPN and PNP, those are used to combine to make digital components that work like our logic gates. And when we create and integrate circuits like the serial and parallel circuits that we talked about in our last module, the serial and parallel circuits, if we integrate enough of those, we have a component called the integrated circuits digital device, right? ICs. And when people just talk about computer chips in general, they're talking about these. Now, these got more and more sophisticated, and the circuits grew smaller and smaller and smaller. So over time, the thing to understand is that transistors became smaller and smaller over the years and more efficient, so that it became possible to duplicate those transistors inside this semiconductor material without using the actual wire and pieces to build NPN. There is a way to etch the silicon so that it behaves like a PNP or an NPN. Let me say that again. After working with transistors for so many years and understanding the two types, NPN and PNP, the materials science advanced to the point where they discovered how to take that raw silicon and oxygen, the silicon dioxide, right? And they take that semiconductor and they work with lasers and fabrication equipment. And what they're doing with that material is creating the NPN, PNP devices and building circuits. And that's where the term integrated comes from. They're putting it all in one big piece of material. Any questions so far?
No.
The one thing I'd like to share with you that's really important to understand is that you can pursue a PhD, a doctorate degree in computer engineering on this topic alone. And so there are many computer engineers that become subject matter experts, and they earn their PhDs and they do research. And this is how we get bigger, better, faster chips, right? So this is one way that happens, is that the materials science is so much more advanced than the progression that's occurred with coding. So when you look at software development, it hasn't occurred nearly as fast as hardware. And it's the hardware science that's so fast and progressive in terms of the technology industry in general. This is where most of our innovations and advances have been made possible, and it's why our software can be a lot of the dependencies that we have for inefficient software and coding techniques really don't matter if we're working on a machine that is the equivalent of the computer that landed the lunar module. So some of us have smartwatches, we have electronic devices, and there's more computing power. There's more computing power in your car right now, more computing power in your car than the computer that was on the Apollo 13 lunar landing module. And that is not an exaggeration. So that's just how far they've come. So it is this setup with materials that differ in terms of how they work with electrons that allow the transistor to switch on and switch off how the electric flows, right? Any questions about what we've shared to this point? So this website is actually a really good resource. And it talks about digital logic gates here. And it also retraces the history of transistor creation and design, and how the older chips were built with something called TTL, right? So the transistor to transistor logic in the early days of computer hardware evolution, essentially the material science could only allow for a certain level of miniaturization. And then over time, they came up with new designs. So the term FET, now it's kind of funny to me because FET in the territory means something different, doesn't it? Yeah. So we talk about field effect transistors. We have a JFET or MOSFET. So over time, the TTL method of building integrated circuits advanced, and these new types of materials, field effect transistors, came onto the scene. So, you know, you have something that can be miniaturized even more or shrunken even more, and it takes less power. So one of the important things to understand is that the older materials took more electricity and were not as efficient and would overheat, right? And the impurities would matter, the level of impurities. And then over time, the materials science advanced to the point where the semiconductor material itself allowed for the construction of field effect transistors embedded in them inside the semiconductor material, right? When we talk about integrated chips or integrated circuits, there's a series of acronyms that you need to become familiar with, okay? So in the early days when we had TTL, integrated circuits, right? This was considered to be small scale integration. It would contain up to 10 transistors or a few gates within a single package, such as AND or NOT gates, right? And then by the time we got to the 50s and 60s, 1950s and 1960s, we started seeing medium scale integration between 10 and 100 transistors. And then later in the 60s and early 70s, large scale integration. So you'd have 100 or 1,000 transistors. So this was a big deal back in the day, because essentially the first calculators. Has anyone ever heard of slide rules? Has anyone ever heard of the term slide rule?
I've seen one, but I guess I didn't realize the name was slide rule.
So even in the 60s, with the first Apollo space missions, the engineers often used mechanical calculation tools. It's a mathematics tool, right? Used to calculate large quantities of numbers, right? So very large numbers when you're working with that. And so it was a very analog or physical process. When we say analog, we mean physical, right? So these were etchings on the rule, and depending on what you were doing, you would slide each of these pieces in and out, and then there'd be an index line, and it would help you calculate very fast. So exponents, roots, logarithms, and trigonometry, right? This was what we used slide rules for. And this was commonplace in the 50s and 60s, well, 40s, 50s, and 60s, right? And eventually, as chips, as the integrated circuits increased in numbers, by the time we get to very large scale integration, what was allowed after the slide rules, earliest Texas Instrument calculator, right? So Hewlett-Packard was a company that built calculators, and so did Texas Instruments. So Texas Instruments and Hewlett-Packard were two companies that took advantage of the VLSI, right? The LSI and VLSI, and they created the first scientific calculators. And one of the things to understand about Hewlett-Packard and Texas Instruments is that they were really early pioneers of the electronics industry. So when people didn't have to depend on slide rules, they could do much more efficient work. And so this was kind of a tipping point, right? So, you know, I'm dating myself here, but this was in the 70s. So computers started to become an interest when calculators could start to graph results and create graphs of the numbers instead of just the numbers, right? And that required even larger chips. So larger scale integration between 1,000 and 10,000. What we want you to understand is that VLSI was really like a tipping point. And nowadays we have huge, ultra large scale integrations of circuits, right? More than 1 million transistors. More than 1 million transistors, okay? And that's hard to fathom. I mean, in 30 or 40 years to go from 1,000 transistors, more like 40 years, 1,000 transistors to 1 million transistors. ULSI is where we are now. And the really important thing to understand besides that is this idea of Moore. So Moore's law Moore was a pioneer in the early days of the electronics industry, and Moore was also involved with Intel. So about the time that Texas Instrument and HP started producing these calculators with graphical displays, a small company named Intel started producing chips, computer chips, general purpose computer chips. And what Moore discovered is that every 18 months to 2 years, the number of transistors doubles. The number of transistors doubles every 18 months to 2 years, in simple terms, which is why computing power has skyrocketed in terms of the CPU chips, right? So the last thing we're going to do before we close today is to look up how many transistors there are in a common processor, okay? So somebody give me Your favorite general purpose processor. Anybody? Does anybody-
Intel.
All right, Intel. The Intel processor, and we'll call it an you want to see what an i9 is? 13th generation?
Sure.
Okay. So an i9 processor, 13th generation, right? How many transistors? Hello?
Whew, that's a lot.
We could say that's ultra large scale integration, right? So every 18 months to 2 years, if you double, there's an old saying, would you rather have $1 million or would you rather have a penny that doubles every day for the next 30 days? Has anyone ever heard that riddle? Which would you rather have, $1 million in hand right now, or a penny that doubles every day for the next 30 days? You have 30 cycles of doubling. So how much do you have after 30 doubles? A lot more than $1 million. The same thing is happening with transistors. So on that note, we'll go ahead and hit the pause button and we'll take up a review of related content on Wednesday. Does anyone have any questions about where we are and what comes next? Thank you for joining us today. Stay safe, stay dry. We'll see you Wednesday. And start reading our Module 4 study guide.